Hello, welcome back to the MCAT grind. This will be the last video here with Organic Chem Chapter 12, Separation and Purification. These techniques comprise 20% of Organic Chem, so hopefully get this through nice and easy. I've summarized the extraction and purification techniques here. Starting from extraction, basically you have this flask that will have the different densities of compounds in here. You shake it, mix it well to make sure they're immiscible compounds. Usually one's nonpolar and one's polar, and usually the nonpolar ones is like less dense, so it will float to the top, but it could go either way. As you put the flask underneath to only take out the bottom layer, usually like the polar one, you can rotovap it to get rid of the water you put in to make it come out. Rotovap basically is a machine where you can let it spin, add some heat to it, and make the water evaporate. Filtration. If you want to separate a solid from liquid, you can just put a little coffee filter on it and then let it drip through. Simply as that. If you want to use vacuum, you can make it suck even greater to suck out extra liquids into the through the filter. Recrystallization basically bases off of the properties of the different the solute itself to make it more pure, because the impurities may not be able to recrystallize. You want to heat it up just enough so it's completely mixed, then you put it on a little stick thing and let it cool naturally. As it cools down, only the pure things create their own crystals. There are some ways to make this a little better by using a little steering stick to gently scratch the side to start forming the little crystal shells to help it recrystal better. Distillation. If you've seen Breaking Bad, that's basically what they're doing to separate two different compound identities based off of their boiling point. One might boil a little faster than another because it has a lower boiling point. But the simple distillations, like this apparatus, only for less than 1 to 50 degrees boiling points, and they must have greater than 25 degrees difference. For example, water boils at 100 degrees, right? So you want to find something that boils either 75 degrees or 125 degrees, like that much of a difference to separate it. Vacuum distillation adds a suction to make everything a lower vacuum state, so they boil a little faster, right? Things boil in vacuum much quicker, so they can boil at a lower boiling temperature. So you can boil for boiling points greater than 150 degrees. Fractional distillation uses a column to help allow, after heating it up, the slightly higher boiling point compound can condensate at these little catching columns to make sure they trap at the elevator and before they heat up and go to outside to another tube. Basically adds right here. Fractional distillation helps to separate compounds that are less than 25 difference in boiling point. Chromatography. There are ways to also separate and identify different compounds. So thin layer chromatography, the simple form, uses a silica or a paper, which is a polar to attract polar compounds. You just dip it into the solution, and you have 3 spots, or more spots depending on how much you have. So you have the solvent front. The solvent usually is nonpolar and travels upwards. The polar stationary front basically says the higher up you travel, you basically travel faster with the solvent. And if the solvent is nonpolar, the ones that moves up the furthest is the nonpolar mobile phase. And the polar ones stationary because they stick to the silica and paper much more. Reverse chromatography, thin layer chromatography, switches the paper for a nonpolar substance, and instead of a nonpolar solvent, you use a polar solvent, so the higher up you travel, the more polar you are. So make sure to not forget which one is which. Thin layer, I always remember thin silica. So that's like the original one. And silica is polar. Reverse, and also we have the RF, basically is the factor of how much it actually travels, and the fraction we can use from the spot, how much ever it travels divided by the solvent front, the maximum traveled part of the solvent, like the liquid layer on the top. For column chromatography, it's basically the same thing as thin layer, but you can pour in more things at a time. The silica gels or whatever gels you want to put in here, they stick and keep the compounds there, and whatever you don't need drips down, and then later you can get rid of the compounds from the beads by using an elute molecule, by using like a polar thing, like a salt, to pour it down and take them away from the beads. That's exactly what ion exchange does. It has the beads that bind, that are positive, that bind to the DNA, so then they can later switch out a new flask and then pour some salt solution to wash down the DNA away from the beads. Size exclusion have silica gels or certain gels that allow the larger ones to kind of slip through, but the beads are just small enough that have little holes in them that like the small ones catch in them, so they travel down a lot slower. So this is like counterintuitive, but size exclusion, basically the larger ones travel down faster. In affinity chromatography, column chromatography, basically they have antibodies specifically to proteins that bind to them, and so acting similar to like the DNA binding, but then afterwards you can wash it down with another solution. Usually it could be another antibody, or it could be something that washes away the protein, that bind to a protein. The problem with that is that if the elution solution might bind too strongly to the protein, and you can't take it apart. So you need to figure out a way to take that protein and extract it. In gas chromatography, it's basically you're heating up or using this gas solution as like the solvent front, and bring whichever binds to the gas strongly, and you can store it on a little chart, and you can determine the molar mass as well as the ratio and the concentration. Liquid chromatography acts similar to a gas. Basically, same thing, you purify by using a pressurized liquid to, and with the help of a computer, designate a stronger pressure to guide where you want the molecules to go. That's pretty much it for the separation and purification.